Sarah Watson did her undergraduate at the University of Kent and a master's degree at the International Space University. She's worked on the geomagnetism team at the British Geological Survey prior to starting her PhD at the University of Reading. She's currently a final year PhD student submitting her thesis in the next couple of weeks, and her current research is focused on comets and their interaction with the solar wind, and she's currently looking for a postdoc related to space weather. So, Sarah, whenever you're ready.
Thank you. And yeah, thanks for inviting me to do this talk. Probably a good time to kind of get all of my research out there before I submit in a couple of weeks. So my title of my talk is using Comet tail disconnections to test a data assimilative solar wind model. I'm going to try and go through most of what I've been doing in the last 3.5 years in the next 20 minutes. So we'll see how that goes. Nope. Okay. So just a bit of background. So comets are leftover remnants from the formation of the early solar system, and they're primarily made from ice and dust. They have two tails associated with them, an iron tail and a dust tail. The iron tail is directly influenced by the solar wind, and it can undergo things called disconnection events, which is when the tail of the comet is completely removed from the nucleus. And these can happen as a result of certain solar wind structures. So, for example, a coronal mass ejection, a solar wind stream interaction region, or a crossing of the heliospheric current sheet. So why do we care about these comets? So currently in space weather, in order to forecast space weather at Earth, we take initial boundary conditions at the sun, and we put these into a heliospheric model, and we propagate these out into the solar system, and this gives us the solar wind conditions at Earth. We can then check whether the model is working correctly or performing correctly by checking the model output against observations at Earth. This is all well and good. This works okay, but if we have the output of our model isn't quite matching what we're seeing at Earth, then there's a huge amount of space where we could have accumulated this error between the sun and the Earth. So it would be useful to have data points upstream of Earth, which would help us kind of identify where the error had occurred. Also, for forecasting space weather, it's not very useful to find out that your model's not working correctly when the solar wind structure's already arrived at Earth. You kind of want to know beforehand. So what comets can do is they cover a wide range of latitudes, a wide range of longitudes, and also distances to the sun. So they can offer in-situ measurements along the Sun-Earth line or at different latitudes, which kind of help update and improve your model to hopefully provide a better model output of the space weather conditions at Earth. So in terms of my PhD, I was using comets to test the HUXt solar wind model. So the HUXt solar wind model is a model that was developed here at Reading, and it takes initial boundary conditions at the surface of the sun, which are produced by coronal models, and it propagates these out into the heliosphere. And you can use this to determine the solar wind conditions at a given point in the solar system. It's primarily used at Earth, but you can do it for other bodies in the solar system as well. And it gives an output of magnetic field polarity and also solar wind speed. But the most beneficial thing about HUXt is that it's really low, it's really computationally efficient, which means that you can use it alongside a technique we call data assimilation. So data assimilation is when you can combine observations taken from a spacecraft, and you can input these into the model to update your initial conditions, and this will provide a better estimate of reality of your model. There is a caveat to this technique in that because it relies on observations, you can obviously only apply this technique to where you have your observations. So most space weather spacecraft are within the ecliptic plane, which is obviously really useful for Earth. but it does mean that you can only update using data assimilation within sort of like the ecliptic region where your observations are being taken. That doesn't necessarily mean that the model's then inaccurate at higher latitudes, just that it reverts back to using the model without data assimilation. So yeah, I'm now going to refer to this as like the DA region, which is when you can use data assimilation in the model output. Yeah, so I'm going to go through some of the case studies which I've used to test the HUXt solar winds model. So first of all, we thought it would be useful to look within the ecliptic plane, as this is where you can apply data assimilation. So the first study was of a comet tail disconnection event, a singular event, which occurred at Comet Leonard back in December 2021. And this disconnection event was actually captured by the stereo spacecraft. You can see it here on the right. And yeah, the disconnection event occurred when the comet was in the ecliptic, which means that when we were looking at the model output at the comet, we could update the output with data assimilation. And this was kind of a good starting point for testing the model in a region where the DA could be applied. So when we ran the solar wind conditions at the comet during this time, we found that the disconnection event was caused by a heliospheric current sheet crossing. And not only did we kind of find the cause of disconnection, but we also found that when we added data assimilation to the model output correlated better with the observation and the timing of the observations and the solar wind structure being in the correct place at the correct time. This was great. We then wanted to expand this a little bit further because this is obviously a singular disconnection event. You can't really gain much from that. So we wanted to look at slightly higher latitudes, so slightly above and below the ecliptic plane, as well as also considering the ecliptic plane. And we wanted to build up more of a statistical analysis of these events, so gather more data. So yeah, study 2 was focused on sort of the mid-latitudinal range, so kind of plus or minus 20 degrees. So what I did was I went through all the stereo A and B data from 2007 to 2023 and identified any comets that were captured in the field of view. I then ruled out any that were kind of like low resolution, or you couldn't really see what was happening, or they were covered up by data gaps and things like that. But I identified 11 comets over this time period, and this resulted in 24 disconnection events in total, because sometimes the comets undergo more than one disconnection event while they're in the field of view. So these events covered all periods of the solar cycle and had, yeah, a latitudinal spread of about plus or minus 20 degrees. So yeah, these are some of the results. So based on the first study, we found that the current sheet crossing was the cause of the disconnection. So we kind of looked again at current sheet crossing. These are the different comets that we were looking at. And the red line on each is the magnetic field polarity at the comet. And the vertical dashed black lines are when we see a disconnection event. And then the gray shaded region is when the comet was in the data assimilation region, so when the model is effectively more accurate than not. So what we found was that every time we saw a current sheet crossing which occurred when we could apply data assimilation, again, there was a disconnection event which followed. So this was actually a one-to-one correlation. However, when you get outside of this region and you can no longer apply data assimilation to the output, this correlation went down to about 50%, which does indicate that maybe that's due to model inaccuracies, but I suppose it could have been something that we don't know quite about, comet disconnection events as well. Yeah. Another thing we found from the statistical study was that there seemed to be like a time delay between when the comet was crossing the current sheet and the onset of the disconnection event in the tail. And this was actually correlated fairly well with the solar wind speed at the comet. So we found for higher solar wind speeds, the quicker the disconnection event occurs, which actually raises a really exciting possibility that we could actually use these comets for identifying the solar wind speed at certain points in the solar system where we currently can't do that with spacecraft. And yeah, the kind of final study I looked at was, obviously we wanted to expand this even further. So the next logical step was to look at even higher latitudes. So this is kind of the region of space which we don't have that many in-situ measurements. We had the Ulysses mission and Polar Orbiter is also going to slightly higher latitudes now. But other than that, most of our observations and measurements are taken within sort of lower latitudinal regions. So this was quite an interesting region to have a look at. So yeah, again, this is just one comet we looked at. So this was Comet 12P Pons Brooks, and this was visible from Earth in 2024. And it was actually visible from Earth for around 4.5 months. So it was quite a long time period, which we could see it for. So obviously the spacecraft that we used before, Stereo, has quite a wide field of view, but it doesn't cover higher latitudes, so you can't see comets at these higher latitudes. So in order to kind of get observational data from the higher latitudes, we needed to rely on another data source. But luckily, this comet was really bright and visible from Earth, so we had a lot of amateur astronomers taking images of this comet almost daily. So you can see the observational coverage down here on the right. So actually, most of our data has come from amateur observations, but it was also captured in the Stereo HI1 and HI2 cameras for about a month, I think, in total. Which kind of helped back up what we were seeing with the amateur astronomers. So yeah, this comet was really highly inclined, which meant it covered a really wide range of latitudes. So it was plus 80 to minus 80 throughout the time that we could observe it for, which was a huge range of latitudes. And this was in 2024, so it was during solar maximum. And yeah, during the 4.5 month period, we identified 15 disconnection events. And here are some of the results. So these are the solar wind parameters estimated by the HUXt model during the 4-month period. So on the top panel, you've got the solar wind speed, and the second panel, you've got the magnetic field polarity, and then you've got latitude, longitude, and proximity to the sun of the comet. So we decided to make it slightly easier to analyze. We kind of split this up into 3 regions. So we've got, again, the vertical red lines are the disconnection events, and this grey shaded region is where we could apply data assimilation to the output. So first of all, we look at the region where we could apply data assimilation. So again, like the previous 2 studies, within this region, the model agreed very well with what we were seeing in the observation, and there was a current sheet crossing, which was followed by disconnection. We also then applied the time delay velocity profile that we saw from study 2, and this event fell within the range of that. So that was consistent again. So again, the model works very well when you can apply data assimilation. Next, we look at this region. So you can see in the second panel is the kind of changing of the magnetic field polarity. And you can kind of see this distinct region in the middle where the magnetic field is changing quite a lot, but outside this region, it's not really changing at all. So we've kind of decided that this is the extent of the current sheet. So the comet was previously above it, and then it was crossing it multiple times, and then it went below it again. So yeah, we focused on this region next, which is outside of the data assimilation region, but within the extent of the current sheet. So similar to kind of study 2, we found that outside of the DA region, the correlation between the model and the observations is definitely less effective. There are some times where the model output, sorry, where the model output does correlate well with the disconnection event. But there's also some times where, for example, the disconnection seems to happen before the current sheet. So this indicates that HUXt has managed to identify that there's a crossing there, but it's kind of got the timing slightly wrong. So whether this is an error in the initial conditions or sort of as propagation of the conditions, I'm not quite sure. Yeah. So finally, we looked at sort of the region outside of the current sheet. This meant that we could then rule out the current sheet as a cause for these disconnection events, because we know that there was no magnetic field polarity changes. So in this region, we identified 6 disconnection events. 5 of these appear to occur near a kind of drastic change in solar wind speed, most likely from a coronal hole or something. However, again, sometimes the timing of this is really quite off. You can see that some of them are quite far away from these solar wind structures. Some of them happen during and some of them happen slightly before, indicating that HUXt can identify the structure, but it just doesn't quite get it, the timing or location of it quite right. Also, this event here that we're seeing, I don't know if you can see my cursor, but the second event in occurs not really near any solar wind change. However, we did identify later that this was most likely due to a coronal mass ejection, which was near the comet at the time of this disconnection. Yeah. I've realized I've gone really fast, sorry. So in terms of, my conclusions, so we tested the HUXt solar wind model at a large range of latitudes using comets as kind of the in-situ probes and our means of testing the model. We found that data assimilation is a really great technique to improve the accuracy of the solar wind models, and observations of these comet solar wind interactions agree better with the model in this region. When data assimilation can't be applied, the model performs definitely a lot less well, and there's less agreement with the observed disconnection events that we're seeing. However, this error doesn't really appear to have any dependencies. Like, it doesn't get any worse. Like at high latitudes, it's more of like a binary situation of like, it works really well when you can apply data assimilation, but when you can't apply data assimilation, it just doesn't work as well. It doesn't work better at certain times of the solar cycle, or if the comet's closer to the sun or anything like that. And yeah, we've kind of realized that HUXt can identify the correct solar wind features, which could be causing these disconnection events, but the timing and sort of the longitudinal location is slightly off. In terms of future work, for me specifically, it's to finish my thesis, which the deadline is 2 weeks. So that's kind of my main priority right now. But in terms of like the research, if it could be continued, that would be great. I'd love to kind of expand it to other data sets. I think we've obviously only used stereo and some amateur astronomers, but Punch was recently launched, and similar to stereo, it has a really wide field view cameras. So we could really expand the data set. And I know that it's already captured a comet disconnection event in, I think, a couple of months ago. So that's exciting. And also other case studies of similar to the 12P Pons-Brooks comet, which come in at really high latitude. So we can investigate the high latitude solar wind a lot better. And finally, which I think is probably a bit further in the future, is that we could actually use these comets as their own in-situ measurements. So we're not relying as much on spacecraft. And we can kind of use the data that we're getting from observing these comets from a distance to update our solar wind models and kind of expand the region where we can use data assimilation to higher latitudes and not just within the ecliptic plane. Yeah, sorry I went quite fast, but thanks for listening, and if there's any questions.